Okay, so we finished all the exponent rules. You know your exponents. You've practiced your exponents. Now let's apply it. So the next thing we're going to do is we're going to look at exponential functions. So the aim is exponential functions. And I'm going to start with an example from science class. I want you to imagine that you have a Petri dish with 5 bacteria in it. There's 5 bacteria. So at time 0, there are 5 bacteria. And what we're going to say is that these bacteria double every minute. They double, times 2 each minute. So that's the rate. So it's a rate, right? And so let's make a chart. Let's make a chart here, right? So this is going to be time. And so number of bacteria. And so at time 0, the initial time, we have 5 bacteria. And then 1 minute later, what is that? Let's see, 1 minute later, how many bacteria do we have? 10. Okay, what about 2 minutes later? What happens to those 10? They double also. And let's continue the chart. After 3 minutes, we have 40 bacteria. And after 4 minutes, we have 80 bacteria. So that's fine, but we want a formula. We kind of see there's a pattern, right? So let's break this down. So 5 is actually, 5 times 1, and 10 is 5 times 2, and 20 is 5 times 4, 40 is 5 times 8, and 80 is 5 times 16. Interesting. Well, I could write this as 5 times, 2 to the 0, right? And then this is 5 times 2 to the first, 5 times 2 to the second, 5 times 2 to the third, and this is 5 times 2 to the fourth. And so I can now, create a formula to represent for any time. I could say that, let's see, the number, let's call it y, is the number of bacteria, and x is time in minutes. And just by looking at this, I can say y is equal to 5 times 2 to the x. Now, what does this represent? The 5 seems to represent the initial value, and the 2 is the growth factor, the initial value, and this is the growth factor. The 2 is the growth factor. And so what we have here is an exponential function. So it's different. This is an x, and this is known. So y equals a times b to the x is known as an exponential function. Okay, and like the linear, we have an initial value, the y-intercept, and a change, right? And so let's just take it on the side a little bit. Y equals mx plus c. This is the y-intercept, and this is the slope or the change. This is the change. And we saw with linear, it just goes up and over, up and over. With a rate here in this example, we're multiplying. Now, the connection is, this should remind you, this is like our geometric sequences. And the lines are like our arithmetic sequences. So that's why I started in the beginning of the year with arithmetic and geometric. Arithmetic corresponds to linears. Geometric connects to today's lesson. So, but I don't want to focus on linear, right? You can put this off to the side. I'm going to erase it because I need the space. So let's continue with this. So what I want you to do is I want you to go to Desmos right now. I'm gonna switch over to Desmos, but you're gonna go to Desmos and you're gonna put this equation in y equals a times b to the x. And I want you to, well, I told you what I want you to do is make some sketches, and I want you to explain, where, what is a. And then what I want you to do is I want you to tell me how B affects the graph. And then what I want you to do also, so when you're creating your slider, maybe you're doing it right now, just make B from 0 to 10. Right? So let's get the sketches down. Okay, so I asked you to explore in Desmos, and because we have a new student in the class, I'm just going to review how to use Desmos. You're going to go to www.desmos.com, and then here you're going to put y equals a times b. To do the caret, I have this thing down here. I can't get rid of it, but you should be able to do, for an exponent, you do shift 6, and that caret is the exponent, put the x up there. The other thing, so we're going to work with sliders because we want to change the value of x and b. So we choose sliders for all. At first, I want you to keep a positive. So click on the a, go from 0 to 5, enter. And then I want you, we'll take that out, and then I want you to look at the b slider, and I want you to go once again from 0 to 5. Okay. Enter. And then I want you to fool around with the graph. So when, what's going on with B, we're interested. So the question, I want to know what makes it, change, and also what's going on with the A. How does the A, changing the A, affect the graph? Okay, the other thing I did mention that I spoke about in the video, something called an asymptote, and I told you to put a plus C in here. And the idea is I'm not going to change the slider, but I want you to tell me what happens. How does the C affect the graph? So I'm not going to put. You can come back to Desmos. So I'm not going to change. But once again, that C is in there. How by changing C, and we can let C be anything from -10 to +10. How does that affect the graph? If you remember, so I just told you to make A and B both positive, and we're only interested in positive A's and B's. Let's just see what happens when A is negative. So let's go back to -5, enter, and let's put B to -5. So the first thing we want to do is, if I move the A over to negative, it kind of like flips it down. It kind of flips it down. And that's known as a reflection. We're not studying that in this class. But what happens when B is negative, when what we call the growth rate is negative? Well, we go to 0. It kind of starts to look weird. And we know just by looking at that, it's not a function. We're not interested in this. Therefore, we're never really interested in the B being negative. Okay, so once again, explore A and B when they're positive, and explore B is C after we talk about asymptotes. Nice. Okay, so once again, you went to Desmos, you put this in, you created the sliders, you come up with 2 graphs. Now, first, I apologize. Make sure that A is greater than 0. So you might want to go back and change that. Okay, so we have 2 things. You should have noticed that if B is between 0 and 1, then y equals a times b to the x is decreasing. And so you should have got a graph that looks something like this. This was your A, and it was decreasing. The other thing you might have noticed is that if b is greater than 1, our y equals a times b to the x is increasing. the graph is increasing, and it looks something like this. Starts off here. Once again, where A is, this is A, and it's increasing. Yeah. Quick side note, what happens when B is 1? Explore. When B equals 1, what happens then? Good. Okay. Well, there's two things you want to notice about these graphs. First of all, well, there's a couple of things. There's, the y-intercept is A. Whatever the A is, that's where the y is. Now, I asked you to keep it positive because in this class we're just going to do real life examples like 5 bacteria, and so we're always starting off with a positive initial value. So keep A positive. So we know that A is the y-intercept. We see it's either increasing or it's decreasing. The other thing you're going to notice is we're going to introduce a new term. And the new term is called an asymptote. An asymptote, and we're not going to really talk about it in this class. If you take SL analysis next year, this idea of the asymptote is that the function comes down and it gets really close to 0, but it never touches 0. So right here, so we say that a graph is, the idea is we have an asymptote for y equals a times b to the x. For this function, I might change this. For us, y equals 0 is an asymptote. And the idea is, you can see it here, although these graphs get really close to it, because although y equals a times b to the x gets very close to y equals 0, they never meet. They never meet. So these two graphs, as it decreases, it gets smaller and smaller, but it never gets to 0. As this goes back towards negative infinity, I'm getting a little fancy here. As we get down, as we go to the left, it gets closer and closer to 0, but it never gets to 0. Therefore, you have something called an asymptote. Okay, let's move on. And once again, if you're interested in the idea of the asymptote, very advanced, what you can do is you can change these and add on a C. If you add on a C, the plus C becomes the new asymptote. So, but once again, we're not covering this class, but if you want to look at the function a times b to the x plus c, you'll see that the graph, it gets close to c, but it never touches it. Okay, let's move on. So, what we're interested in, So the next thing we're interested in how it changes, because that's what we studied in linear equations. We say, y, you would say, y equals 2x plus 5, and you would say how we know it's so we look at this function, we know it's increasing. The next question was, how is it increasing? You would say, oh, you go up 2 to the right 1, up 2 to the right 1. That's fine. The question now is, how are exponentials increasing or decreasing, or more specifically, by what rate? So the question is, by what rate are the exponential functions increasing or decreasing? And this it's like an interesting question, because if you think about it, once again, go back to the linears. How about we compare, y equals 2x plus 5 versus y equals 3x plus 5? And so you might say, oh, well, Mr. Elliott, they're both increasing. But I'm going to say, wait a minute, are they both increasing the same? And you go, no. The language we had was, 3x is more steeper, or it's increasing faster. Okay? We can apply that same thing to exponentials. Okay, so let's take a look at our function, y equals a plus b to the x. Now, the idea is, I know the a is the initial value. I want to know how the b is changing. I know I can just look at that number, whether it's increasing or decreasing, but I want to know by how much. Well, what you're going to do is you're going to take your b and set it equal to 1 plus or minus 3. And this r is going to be your rate. Example. So if I give you y equals 500 times 1.37 to the x, so what do we see here? Well, I know we're starting off at 500. Maybe it's deer, or maybe it's gold or something like that. Or maybe it's money. And I know the growth rate is the growth factor is 1.37. So this is initial. This is the growth factor. But I want to know by how much it's changing. I know it's increasing. I know 1.37 is greater than 1, so it's increasing, but by how much? So I'm like, okay, 1.37 is equal to 1 plus 0.37. It's increasing by 37%. And that's what this number tells us. Let's look at another example. How about y equals 350 times 0.83 to the x? You look at that equation. Well, let's make up a story. Maybe it's 350 rhinoceroses, and the growth rate factor is 0.83. Well, is this population increasing or decreasing? And you'd say, well, because 0.83 is less than 1, it's decreasing. So, and we can easily figure out when this is going to happen. I just want to know, at what rate are these rhinoceroses decreasing? You'd say, okay, I know that 0.83 is equal to 1 minus 0.17. Therefore, it's decreasing at a rate of 17%. And let's try another one. Y equals, 210 times 1/2 to the x. You're going to study this in chemistry. This is known as the half-life. So, for example, some chemical loses half its molecules after an hour. Well, at what rate is it so we know it's decreasing. At what rate is it decreasing? You're like, okay, 1/2 is equal to 1 minus 1/2. Therefore, it's decreasing at a rate of 50%. Now, kids are fine with this. Kids like decreasing, and they like this until let's go back to our original problem. Y equals 5 times 2 to the x. So we know that we started off with our bacteria. How are we doing for time? Good. We started off with we started off with 5 bacteria, and we used the word doubling. Well, what does that mean? Well, we know it's increasing. Well, by how much? Okay. Well, 2 is equal to, how are we going to write that? Very good. 1 plus 1. That means we're increasing 100%. Kids get weird because when I say doubling, they say, no, when you double, it's increasing by 100%. And so that's how we figured out the rates. And so I think that's basically it. Yep, let's say everything. And so So if our R is greater than 0, we call it exponential growth. If our R is less than 0, we call it exponential decay. Sorry, decay. So, yeah, that's basically, so you can start to create these word problems. So I want you to, so let's see. So in every problem, once again, a plus b to the x. First, find the, look for the word rate. Look for the word rate. Okay, and then second, identify initial value and the rate, and then the equation. The equation is y equals a times 1 plus or minus r to the x. Now, I combine these lessons together. Once again, the initial value. You have to determine if it's increasing or decreasing. And you're going to see words like, so if it's increasing, you're going to see words like appreciate, growth. If it's decreasing, if they say the rate, it's decreasing at a rate of, that you have to subtract, and the words are depreciate and decay. And that's basically it. See what you can do. And also you have to practice your obviously, you have to turn your percentages back to decimals. And that's, so remember, like 15% has to be written as 0.15. If you're nervous and putting in the calculator, just take any number. So for example, it's like 7.39%. Just write this as 7.339 divided by 100. That you can do that. Or if you're good with this, you can write this as 0.0739. Good. Okay, I just want one last thing. Just remember, for any of the word problems, they're all going to be in the form of y equals a plus b to the x. And so once again, you're going to be given an initial amount. And either b, this is the factor, or it's going to be like 1 plus or minus a rate. So you're going to look for these important words. So and once again, connecting it with the vocabulary that we did. So if it's a rate that appreciates or depreciates, that's the R, the rate. But if you're talking about a factor, that's the entire B. And so you're going to see on the word problems tonight. So for example, number 9, they talk about a population that increased, the annual rate of increase is 1.29. That's the R plus the R. Number 15, we're going to talk about a computer that depreciates at the rate of 14.3. That's minus the rate. And then, so that's the basic word problems. Once again, you're looking for an initial amount, and you're looking for the rate to create the factor. Once you do that, you're in good shape. And then, yes, number 56, if you want to do that one, we talk about, they tell you has the factor of 0.75. So they tell you the B. They tell you after 6 years, the final amount is 1. So once again, what I didn't talk about, this is the final amount. So how about we do 56? The value of an industrial machine has a decay factor of 0.75 per year. After 6 years, the machine is worth 75,000. So we don't have the A. We would use you would use your GCD to solve it. But once again, this idea, they gave you a factor, they gave you time, and they gave you the final amount. They're asking you to find the initial value. And that's how we solve these word problems. So once again, it always comes back to y equals a plus bx. Final amount is equal to the initial amount times the growth factor, which is 1 plus or minus r, to the time. Good.